So now we have these two inequalities which will help us estimate our Dini derivatives. So I claim that if I set un to be the union of k and j greater than or equal to 1, I, k, n, j. So I am taking the union over all k and all j, then E, Q, Q intersection with the set In. Remember that In was one of the open intervals constituting the set U, open set U, which covered E, Q, Q, and on which we applied the first application of the rising sun lemma. And this set is a subset of Un, and Un is a subset of In. The measure of Un is less than or equal to Q over Q, small q over capital Q, times the measure of In. So let's see why these claims are true. Now to prove the first part, let x be a point taken outside Un but inside In, and let y be a point strictly greater than x inside In. Then what we get is that f of q of y is less than or equal to fq of x, again by the rising sun lemma, because these are points in the sun. So this implies that fy minus qy is less than or equal to fx minus qx, and this is nothing but fy minus fx over y minus x is less than or equal to q. So this implies that the lim sup of h going to 0 with h positive, fx plus h minus fx over h is less than or equal to q, and this is nothing but the upper Dini derivative of the positive part. This is less than or equal to q, which implies that x does not belong to EQQ intersection In, because on this set the upper Dini derivative must be strictly greater than q. So this means that EQQ intersection In is a subset of Un. So this proves the first part, and for the second part we argue as follows. So for the second part we have m of Un, which is nothing but the sum k j greater than or equal to 1 m of I k n j, and m of I k n j is less than or equal to 1 over capital Q, again sum over k j greater than or equal to 1 f of bkn j minus f of akn j. We have already established this relation, and since f is monotonically non-decreasing, we have that this is less than or equal to 1 over q. We can sum over j, and if you just sum over j, then is going to be less than or equal to f of bkn minus f of akn. And now again, because of the rising sun inequality that we had earlier, this is less than or equal to q over q, k greater than or equal to 1, m of I k n, but this is the set q over q m of E n, and this is less than or equal to q over q m of I n. This is a disjoint, because E n was the disjoint union of I k n, k greater than or equal to 1, disjoint union. So we get our result that mun is less than or equal to q over small q over capital Q over times m of I n. And now we can finish the proof. So we have m of e q q, this is equal to the sum of m e q q intersection I n greater than or equal to 1, and this is less than or equal to, so this is a subset of un, remember, and so this is the sum over m of un, which is less than or equal to q small q over capital Q and greater than or equal to 1 m of I n. And now these I n's are precisely the decomposition of the open set U that we took. So this is nothing but q over q of m of u, but mu was chosen so that this is less than q over q times me times q capital Q over small q. So this cancels out, and so you just get me, so meq, meq, here also meq, and so they have a strict inequality between meq and meq, which is a contradiction, which proves the result. So this finishes the proof for continuous, so differentiation theorem for continuous monotonically non-decreasing functions. It establishes the almost everywhere differentiability for such functions. And now I am just going to state what happens for monotonically non-decreasing functions which might have discontinuities. Now finally, let me just state the theorem where we can drop the condition for continuity of the monotonically non-decreasing function, and this is a sort of a structure theorem for monotonically non-decreasing functions. So the first one says that if you have a monotonically non-decreasing function f, then it has countably many points of discontinuity at xn. So it's a collection of countably many points in AB where the function f might be possibly discontinuous. And secondly, it can be expressed as a difference of two functions fc and fpp, where fc is continuous and monotonically non-decreasing, and fpp, so pp stands for pure point, and it is it's a sum of countably many what are called jump functions j and x. So each jump function is given by this formula: j and x is 0 if x is less than xn. So this is the point of discontinuity, and at the point of discontinuity it takes the fractional value of the jump that f has. So for example, so if this is xn, then f comes from the left, of xn, but it might take a value higher than strictly higher than the limit, the left hand side limit, and then again because it is increasing there will be a right hand side limit, and so this fraction of the entire length is given by this formula here, and so the jump functions are encoding this kind of finite discontinuities in the function, and so this FPP is a sum of countably many such jump functions with amplitude precisely this alpha n, which is the difference of the left and right hand side limits. So in fact this pure point function FPP is differentiable almost everywhere and vanishes, the derivative vanishes almost everywhere, and since we have already proved that this one is since it is continuous and monotonically non-decreasing, it is differentiable almost everywhere, so then f is differentiable almost everywhere. So for all these proofs I will refer you. So for the proofs, reference is Stein and Shakarchi's book, Shakarchi, section 3.3, where you will find the detailed proof for these results. So this finishes our discussion for the differentiability theorems for functions which are of bounded variation as well as functions which are monotonically non-decreasing. Finally, let me just say some concluding remarks about the second fundamental theorem of calculus. Second fundamental theorem of calculus. So it says that if f from AB to R is differentiable and f prime is Riemann integrable, then the integral a to b of f prime x dx is nothing but fb minus f of a. So we can try to ask whether even if we have, let's say, a continuous function which is in L1 over AB and which is differentiable almost everywhere in AB, then whether such a formula holds. First of all, a continuous function may be nowhere differentiable. An example is given by the so-called Weierstrass function, which is given by this sum sine of 8 to the power n pi x, and so this is defined over 0, 1 to r, and one can show that this is nowhere differentiable in this interval 0, 1. On the other hand, there are continuous functions which might be differentiable almost everywhere, but for which these kinds of functions, these kinds of equations do not hold if we replace the Riemann integral by the Lebesgue integral. So even if we have a differentiable, almost everywhere differentiable function f, for which the derivative is in L1, then even in that case it's not true that the Lebesgue integral of f prime gives you fb minus fa. So a counter example is given by the Cantor function on the defined using the Cantor set, and for this function, the derivative is 0 almost everywhere because it's constant almost everywhere. So the derivative is 0 almost everywhere, but f0 is 0 and f1 is 1. So the left hand side is 0, but the right hand side is 1. We make the following definition for absolutely continuous functions. So this is a function f, and it is said to be absolutely continuous if given epsilon greater than 0, there exists delta greater than 0, such that we have the following condition that if there exists finitely many open intervals, disjoint open intervals a, k, b, k, so this is a finite collection of disjoint open intervals in a, b, such that the total length of this union is bounded by delta, then the variation, so this is a sort of a variation of f over these intervals is less than epsilon. So these are called absolutely continuous functions. Now note that absolutely continuous functions are continuous and in fact uniformly continuous on AB, and the point is that for absolutely continuous functions, the analog of second fundamental theorem of calculus holds for the Lebesgue integral. And so the point is here is that the second fundamental theorem of calculus will hold for absolutely continuous functions. So if you have an absolutely continuous function on a compact interval AB, first that f is differentiable almost everywhere, f prime is an absolutely integrable function on AB, and thirdly that the integral over AB of f prime is precisely fb minus fa. Now the first two are actually consequences of the fact that absolutely continuous functions are of bounded variation. So we have shown that for a function of bounded variation, it is differentiable almost everywhere. It's also true that the derivative of the bounded variation function, which is defined almost everywhere, is in fact an L1 function. So this third part is where the absolute continuity plays a role, that the second fundamental theorem of calculus holds. So we come to the end of this topic about differentiation theorems.